Hello and welcome to Group 5's Collaborative Research Project presentation. The topic we chose to research was the implementation of nuclear power as a cleaner energy alternative. Here's a brief overview of our presentation organization. In our work, we will cover the history, operation, input, and ethics of nuclear power plants and compare them to fossil fuels and renewable alternatives. Our team is composed of 6 members: Kaylee, who will be presenting the introduction, Yuji, who will tell us the history, Sierra, who will talk about how power plants work, myself, Alexandria, who will be comparing the output of nuclear plants to other energy production methods, Han, or also known as Ryan, who will be covering the ethics of nuclear energy, and lastly, Christopher, who will conclude our presentation. To begin our presentation, I will let Kaylee introduce us to the need for nuclear power.
To give an introduction to why nuclear power is needed in the first place, today's global economy largely relies on energy produced from burning fossil fuels. This process emits large amounts of carbon dioxide as a byproduct, and scientists widely recognize that increasing levels of carbon dioxide is a major contributor to climate change. Despite reduced economic and human activity from the COVID-19 pandemic, global carbon dioxide emissions only increased in 2020, leading it to become one of the warmest years on record. These rising global temperatures have had drastic effects, contributing to more frequent and severe extreme weather conditions, such as cold and heat waves, floods, droughts, wildfires, and storms across the world. The need to mitigate carbon emissions is critical, with many countries aiming to reach net zero emissions by 2050. Experts have argued that the most cost-effective strategy is to deploy a range of alternative energy technologies. One such clean energy alternative is nuclear energy. As of March 2021, nuclear energy provides 10% of the world's total electricity from over 440 power reactors. It is the world's second largest source of low-carbon power, and the global market is only expected to grow from $103 billion in 2020 to $118.5 billion by 2025. Nuclear energy is harnessed from nuclear fission, the process of splitting atoms in a reactor to produce energy. Fission releases heat, which is then used to create steam that spins a turbine and generates electricity. Uranium is used as fuel instead of fossil fuels, which does not emit a large amount of carbon dioxide. So nuclear energy is considered a low-emission, clean energy source. And now I'll be handing it off to Yuji.
Thank you, Kaylee. My name is Yuji Moida, and I'll be presenting about the history of nuclear power. Following the discovery of uranium in 1789, the science of atomic radiation and nuclear fission was pioneered from 1895 to 1945. Most research into harnessing nuclear fission was motivated by military applications. From 1942 to 1946, the United States, the United Kingdom, and Canada pioneered the development of nuclear weapons through the Manhattan Project, which prefaced the deployment of nuclear bombs in Hiroshima and Nagasaki, Japan during World War II. Through the development of nuclear weapons, scientists realized that heat produced through nuclear fission could be harnessed to generate electricity. So on December 20th, 1951, the world's first nuclear reactor for electricity generation was switched on to power the city of Arco, Idaho. In the years since, other countries across the world have built and employed nuclear power plants as an energy source. Today, there are about 440 nuclear power reactors operating in 32 countries, which supply over 10% of the world's electricity. Nevertheless, nuclear accidents have occurred and resulted in significant effects contributing to public hazards. The 3 most prominent nuclear disasters are Chernobyl in Ukraine, 3 Mile Island in the United States, and Fukushima Daiichi in Japan. As a result of each disaster, safety precautions have evolved and been implemented as a prevention measures against future nuclear disasters. This Chernobyl nuclear power plant housed 4 nuclear reactors and was one of the most important sources of power in Ukraine. On April 26, 1986, one of the worst nuclear disasters occurred due to an unstable and uncontrollable reactor, which resulted in an explosion. The personnel controlling these reactors were not following correct operating protocols and disabled automatic shutdown mechanism, which contributed to the accident. The reactors themselves were not designed to operate at a high power output, resulting the radiation exposure blanketed some 200,000 square kilometers, including Ukraine and the surrounding areas. Thousands of people were sickened by disease and radiation poisoning, forced to live with the consequences and long-term effects for the rest of their lives. The 1986 Chernobyl disaster demonstrated how even with added safety measures in place, nuclear power plants are still at risk for accidents due to flawed reactor designs and inadequately trained personnel. On March 28, 1979, a mechanical or electric failure started a series event that led to a partial meltdown at a reactor at 3 Mile Island in Pennsylvania, United States. Personnel did not realize that reactor was experiencing a loss of coolant and unknowingly worsened the issue. After the 3 Mile Island accident, public support for nuclear energy declined from an all-time high of 69% in 1977 to 46% in 1979. An estimated 2 million people were exposed to small amounts of radiation as a result of the 3 Mile accident. Federal requirements for safety controls and emergency response planning became more stringent, and officials imposed a temporary moratorium of the licensing of all new reactors. As a result, the construction of nuclear reactors steeply declined. In March 2011, the Fukushima Daiichi nuclear power plant located in Futaba district of Fukushima Prefecture, Japan, catastrophically failed. A 9.0 magnitude earthquake caused vast structural damage, the loss of many lives, and a 15-meter tsunami to crash onto the shores of an already devastated island. In the following 46 days, the air, water, and land were contaminated with radioactive debris as a result of the melting core. Over 100,000 people who were affected by the radioactive exposure had to be evacuated from their homes in the surrounding areas. As a result of the explosion in Fukushima, information about nuclear energy was broadcasted on every major news, and nuclear energy became a topic discussed around the world. The benefits and potential dangers of nuclear energy were debated extensively by scientists and politicians. The accident prompted other countries to review their nuclear energy policies. The German government vowed to phase out nuclear power within 10 years and replace it with renewables. Switzerland also decided to not build any new reactors and to stop producing nuclear power by 2035. Safety is paramount at nuclear power plants, and facilities currently incorporate a well-developed and much-tested set of safety procedures. It is important for the government to improve system protection and emergency response for the future. Now I will be passing it off to Sierra.
Thanks, Yuji. I'm Sierra, and I'll be going over the life cycle of nuclear fuel and how nuclear power plants generate energy. The life cycle of nuclear fuel begins with mining the uranium. In the United States, most uranium is mined from sandstone deposits in similar locations as coal mines in Wyoming and the Four Corners area. The uranium mining process has similar environmental impacts to coal mining, with the additional hazard of polluting groundwater, with traces of radioactive material and heavy metals. U-235 is the form of uranium that can be processed into fuel for nuclear power plants and is relatively rare, composing less than 1% of the uranium found in nature. After the ore is mined, the uranium is leached from the ore using acids and converted into U-308, the form of uranium used for fuel. This is molded into small ceramic pellets, which are assembled into fuel rods. The fuel rods are packed into fuel assemblies and then sent to the nuclear power plants ready for use in the reactors. Nuclear reactors generate power through the process of nuclear fission. During this process, atoms of uranium collide with neutrons and then split, releasing large amounts of energy. This energy heats the water surrounding the fuel assemblies, and the resulting steam spins the turbines connected to generators to produce electricity. The steam is then condensed into liquid water in either a cooling tower or using water from nearby lakes and rivers. Two main types of nuclear reactors are boiling water reactors and pressurized water reactors. Approximately 2/3 of the reactors in the United States are pressurized water, while the remaining 1/3 are boiling. While both reactor systems use water from outside sources, their differences lie in which water source is used for steam. Boiling water reactors use the same water heated by nuclear fission to spin the turbines. First, water in the boiling chamber is heated and then turns to steam. The radioactive steam is channeled out of the containment structure, where it is used to spin the turbines connected to a generator, supplying power to the nearby community. This radioactive steam is then cooled using a non-mixing heat exchanger with clean water from an outside source. The clean water steam is then sent to a cooling tower to be cooled into liquid water for reuse. Pressurized water reactors use the water from an outside source to turn to steam to keep the radioactive water separate within the containment structure. The water surrounding the fuel assembly rods is heated under pressure, remaining in the liquid phase, and this radioactive water flows through a steam generator to heat non-radioactive clean water, which turns to steam and then flows through the turbines. After passing through the steam turbines, the steam is cooled to liquid water using water from an outside source, similar to the process in boiling water reactors. Both types of nuclear reactors operate to produce a high energy output
while sustaining a smaller carbon footprint in comparison to fossil fuels and other energy production methods. Now I'll hand it over to Alex to go over the energy output of nuclear power compared to other energy options.
Thank you, Sierra. Now to take a look at energy output comparison. Nuclear power plants offer a lower carbon emission energy source that partially meets current global power consumption demands. Globally, coal and gas are the main sources of energy output and make up over 60% of the world electricity production. Fossil fuels produce the highest amount of CO2 emissions and are a limited resource. Renewable energy sources such as solar, wind, and hydroelectric energy generally lead to little to no greenhouse gas emissions. Due to a combination of technological advancements, public policy, and adequate financing, renewable energy generation increased by approximately 140% from 2000 to 2019. By the beginning of 2020, renewables were responsible for nearly 28% of global electricity generation. Renewable plants, however, are intermittent sources, and a regular supply of wind, sun, or water would require plants to have backup power sources, posing challenges for integration with the present grid energy infrastructure. To enhance their reliability, renewable energy systems can be combined with nuclear plants in order to better meet energy consumption needs. Unlike renewable energy sources, nuclear energy can provide reliable and continuous power in a variety of geographies and climates. According to the United States Department of Energy, nuclear power plants require less maintenance and are designed to operate for typically 1.5 to 2 years before needing to refuel. This contributes to nuclear energy having the highest capacity factor, or average percentage of time for which the power plant is operating at its full capacity annually, of any other energy source. Moreover, the land footprint of a typical nuclear power plant is several times smaller than equivalent capacity fossil fuel plants and renewable farms. The cost of nuclear power plant implementation can be split into 3 categories: capital costs, operation costs, and external costs. Capital costs include the planning, construction, materials, and labor of building a nuclear power plant. Operation costs include obtaining the fuel rods, operation or maintenance, and waste disposal. Lastly, external costs are a cost to society, which would include a potential disaster that surpasses the amount of insurance that would be able to cover. This leads us to the more ethical concerns regarding public and worker safety. I'll now hand the presentation over to Han to further analyze the ethical concerns regarding nuclear power.
Thank you, Alex. My name is Han Chang, or Ryan, and I'll be presenting on nuclear power ethics. This is an important topic to discuss, given the events that surround nuclear energy throughout history, such as accidents that had harmful and radioactive effects, or bombings that destroyed cities and killed thousands of people. When harnessing an immense amount of energy, like nuclear energy, moral principles and values have to be taken into consideration for ethical actions. One of the ethical issues with nuclear power is worker and public safety. Because working with nuclear power and nuclear radiation exposure is so dangerous, safety is always the #1 priority. After the Chernobyl incident in the 1980s, instrumentation and control safety protocols were installed to regulate and monitor nuclear reactor emergencies. Its purpose was to control reactivity, cool fuel in the plant, and contain radioactive substances such as uranium. And from an ethical perspective, the main goal was to implement these safety precautions and protect everyone from danger while the plant was still in operation. Other than ethics of safety in the workplace environment, the ethics of nuclear weapons was also very controversial. Before nuclear energy was used as electricity, it was used for nuclear weapons, most notably the atomic bomb in World War II. The bomb was detonated on Hiroshima and Nagasaki in Japan during 1945 to end the war. Although the war ended, it violated the ethics of endangering the safety and welfare of the public. This unethical action resulted in thousands of deaths, long-term radiation effects, and jeopardizing many lives. And lastly, using nuclear energy to produce electricity releases greenhouse emissions into the atmosphere and elevates global temperatures. Some of the toxic pollutants are sulfur dioxide, shown in this table here, that can produce acid rain and harm the environment, and nitrogen oxides that produce ozone in the atmosphere and weaken vegetation growth. However, when comparing to other energies such as solar and coal, the ethical concerns for nuclear energy aren't that severe. For example, coal creates 700 kilograms per kilowatt hour of emissions, while nuclear only produces 33, which is significantly less than coal. And all of these factors contribute to nuclear power ethics and how nuclear power affects the world. Now Chris will summarize and conclude our presentation.
Thanks, Ryan. To conclude this presentation, I'd like to begin with the motivating reason for discussing nuclear power, and that's climate change. This is from the Intergovernmental Panel on Climate Change, a body of experts that are tasked with designing reports for decarbonization pathways. If current trends continue, compliance with climate objectives will require a 6-fold increase in global nuclear capabilities. So why is this? First of all, nuclear power is a low carbon source of energy, and it is therefore well poised to address the intermittency issues that renewables face. Why is this? First of all, while renewables will play a vital role in decarbonization pathways, we still need to have a baseline load of electricity to supply power when renewables aren't functioning. Obviously, if we want to decarbonize, we cannot rely on fossil fuels, and therefore nuclear power can fill this gap and create the stable load that societies need. Second of all, nuclear power is a mature technology. As Sierra mentioned, boiling water reactors and pressurized water reactors have been around for decades. In addition, nuclear power plants have a relatively low land footprint when compared to, say, coal-powered plants, natural gas-powered plants, or wind and solar farms. In addition, nuclear power plants have the highest operating capacity of any energy generation source we have. So the question is, given these emissions reductions potentials and good performance, what's holding nuclear power back? And the answer lies in ethics. 3 Mile Island, Chernobyl, Fukushima, these accidents are still burned deeply into the public's understanding of nuclear power. And that's not to mention the use of nuclear weapons during World War II and subsequent demonstrations of them. Case in point, nuclear power, when mishandled or inappropriately used, can lead to massive destruction and loss of life. And in addition, as Ryan mentioned, nuclear power can still create externalities like criteria pollutant emissions. And it's concerns like these that hold nuclear power back. The technology is there, the engineering is there. The designs have been worked on for decades now. But the largest obstacle is the court of public opinion. And to move forward and address these concerns while still pursuing decarbonization pathways, we need to make sure that the public is well educated on the state of nuclear power today, as well as the comparative risk between using nuclear power and, for example, a natural gas-fired power plant or a coal power plant, as well as where nuclear power fits into our decarbonization future. Thanks for listening, and I'll hand it back off to Alex to close the presentation.
Thank you, Christopher. Nuclear energy seems to be the most promising energy alternative in terms of efficiency and meeting consumption needs. It'll be interesting to see if nuclear power will be integrated more in the future. Thank you all so much for tuning into our presentation. We hope that this has been an informative and helpful look into the intricacies of nuclear energy implementation. Please feel free to check out our full research paper for more details and references. Thanks again and have a wonderful day.